Here is today's problem. We are presented with a straightforward exponential mathematical equation. The equation features two identical terms being added. On the left side of the equation is 4 to the power x. We are adding another 4 to the power x to that term. The sum of these two terms on the left is 100. Our primary goal is to find the exact value of the variable x. We will solve this algebraic equation by factoring its base terms. We will proceed by manipulating the properties of the given exponents. Let us closely examine the base of our exponential terms. Both of the terms have a numerical base of exactly 4. We can rewrite the number 4 as a smaller prime number. The number 4 is precisely equal to the number 2 squared. We will substitute 2 squared for the number 4 everywhere. The very first term transforms into 2 squared to the x. The second term also becomes 2 squared to the power of x. We must now apply a fundamental rule of exponents right here. When a power is raised to a power, we multiply the exponents. We multiply the inside exponent by the outside letter x. This multiplication gives us a new exponent of 2 times x. Our first term easily simplifies to 2 to the power 2x. Our second term also simplifies to 2 to the power 2x. The full equation is now slightly different but equivalent. We write 2 to the 2x plus 2 to the 2x is 100. We will utilize a standard algebraic substitution to rewrite the current terms. An algebraic substitution replaces terms with temporary placeholder variables. It transforms complex expressions into very familiar shapes. We will define a completely new variable and call it letter u. We carefully set u equal to 2 to the power of the variable x. We now need to figure out how to replace our existing terms. We know that 2 to the power of 2x is essentially a square. It is mathematically identical to 2 to the power of x squared. Because of our substitution, we can replace this with u squared. The very first term in our modified equation becomes u squared. The second identical term also naturally becomes u squared now. We can write our new simplified equation using the variable u. We have u squared plus u squared is equal to 100. We can combine these two identical terms on the left-hand side. Adding u squared to u squared simply gives us 2u squared. Our current equation states 2u squared equals 100. Let us prepare to write this as a standard quadratic equation. The standard quadratic form requires all terms on the same side. We need the other side of the equals sign to be exactly 0. We achieve this by subtracting 100 from both sides. The left side becomes 2u squared minus 100. The right side is 100 minus 100, which is 0. We now have 2u squared minus 100 is equal to 0. To make calculations simpler, we divide every single term by 2. 2u squared divided by the number 2 is simply just u squared. 100 divided by the number 2 is exactly 50. 0 divided by the number 2 remains as exactly 0. Our fully simplified quadratic equation is u squared minus 50. This entire expression is strictly equal to the number 0. We will use the standard quadratic formula to find values for u. The quadratic formula solves polynomial equations of degree 2. The standard algebraic form is a u squared plus bu plus c is 0. We must correctly identify the numerical coefficients of b and c. The coefficient a is the number directly in front of u squared. In our current simplified equation, the exact value of a is 1. The coefficient b is the number directly in front of the letter u. We obviously do not have a regular u term in our current equation. This mathematically means the precise value of b is exactly 0. The constant term c is the plain number standing by itself at the end. In our specific equation, the value of c is negative 50. We will now write down the full quadratic formula for reference. The formula states that u equals negative b plus or minus a root. This root is the square root of b squared minus 4 times a times c. This entire numerator expression is then completely divided by 2a. We are fully ready to plug our identified values into this formula. First, we substitute our value of exactly 0 for the letter b. Negative 0 is mathematically the exact same thing as plain 0. Next, we calculate the b squared portion inside the square root. 0 raised to the second power is also just the number 0. Then we calculate the term minus 4 multiplied by a multiplied by c. We multiply negative 4 by positive 1 to get negative 4. We then multiply negative 4 by negative 50 to get 200. A negative number multiplied by another negative yields a positive. The entire expression inside the square root is 0 plus 200. This simply means the square root part is the square root of 200. Finally, we must calculate the denominator of our large fraction. 2 multiplied by our value of 1 is just the number 2. Our working equation for the quadratic formula now looks like the following. We have u equals plus or minus the root of 200 over 2. We need to mathematically simplify the square root of 200. The number 200 can be factored into 100 times 2. We chose these specific factors because 100 is a perfect square. The primary square root of the number 100 is exactly 10. We can effectively pull this 10 outside of the square root symbol. The square root of 200 perfectly simplifies to 10 root 2. We substitute this new term back into our working expression for u. We now have u equals plus or minus 10 times the square root of 2. This entire quantity is still being divided by the denominator of 2. We can divide the outside number 10 by the denominator number 2. 10 divided by 2 mathematically gives us exactly the number 5. This cleanly leaves us with u equals plus or minus 5 root 2. We currently have two possible mathematical solutions for our variable u. The first calculated possibility is positive 5 times root 2. The second calculated possibility is negative 5 times root 2. We must now actively remember the original definition of our variable u. We purposefully defined u as 2 raised to the power of the variable x. An exponential function will naturally evaluate to a positive real number. We naturally reject the negative option because it falls completely out of bounds. This leaves us with only the valid branch of u equals positive 5 root 2. We now write the equation 2 to the power x equals 5 root 2. We need to correctly extract the variable x from its current position. Taking a standard logarithm of both sides will flawlessly achieve this. We will apply the natural logarithm function to both sides of the equals. The left side becomes the natural logarithm of 2 to the power of x. The right side is the natural logarithm of 5 times the root of 2. We use the powerful logarithm power rule on the left-hand side. The exponent x can be freely moved to the very front as a multiplier. The left side elegantly transforms into x times the natural log of 2. We must isolate x by dividing both sides by the natural log of 2. We get x equals natural log of 5 root 2 over natural log of 2. This is a mathematically valid answer, but we will reduce it into simpler terms. Let us closely examine the complex numerator of our current fraction. We have the natural logarithm of the product 5 times root 2. The standard product rule for logarithms splits this product apart. The log of any product is simply the sum of the individual logarithms. We rewrite it as natural log of 5 plus natural log of root 2. We can easily simplify the natural logarithm of the square root of 2. The square root of 2 is identical to 2 raised to the power 1/2. The logarithm power rule lets us move the 1/2 to the front again. It correctly becomes 1/2 multiplied by the natural log of 2. The numerator is now natural log of 5 plus 1/2 natural log 2. We place this entire expanded expression back over our log denominator. We separate this fraction by dividing each top term by the bottom term. The first separate part is natural log of 5 over natural log of 2. The well-known change of base formula simplifies this exact fraction. It cleanly condenses into the logarithm base 2 of the number 5. The second separate part is 1/2 natural log 2 over natural log 2. The natural log of 2 completely and cleanly cancels out of this term. This cancellation elegantly leaves us with just the simple fraction 1/2. We add these two simplified parts together to get our final value for x. The variable x is strictly equal to log base 2 of 5 plus 1/2. This exact and rigorous mathematical expression is our final valid solution. We can also easily calculate a decimal approximation for our final answer. We need to accurately estimate the value of log base 2 of number 5. We clearly know that 2 to the second power is strictly equal to 4. We also know that 2 to the third power is strictly equal to 8. The number 5 structurally lies right between the numbers 4 and 8. Therefore, the exact logarithm value absolutely must lie between 2 and 3. The number 5 is much closer to 4 than it is to the number 8. This logically means the logarithm will be much closer to 2 than to 3. A precise scientific calculator tells us the natural log of 5 is 1.6. To be slightly more mathematically precise, it is about 1.609. The natural log of 2 is calculated to be roughly 0.693. We divide 1.609 by the value 0.693. This division process gives an approximate decimal value of 2.32. We must crucially remember to add the remaining fraction of 1/2 to this. 1/2 is written in standard decimal notation as 0.5 exactly. The final estimated decimal value for x is roughly 2.82. This decimal approximation shows the approximate magnitude of the real answer. Now we will swiftly return to working entirely with our exact algebraic values. We should formally verify this exact result to ensure it is completely flawless. We will substitute this full value of x directly back into the original equation. The very original problem utilizes 4 raised to the power of our variable x. We substitute our entire logarithmic solution straight into the exponent of 4. We now have 4 raised to the log base 2 of 5 plus the fraction 1/2. Addition inside an exponent indicates that we can multiply 2 distinct bases. This mathematically splits into 4 to the log base 2 of 5 times 4 to the half. Let us evaluate each of these 2 distinct mathematical parts independently. 4 raised to the power of 1/2 is absolutely identical to the square root of 4. The principal positive square root of the simple number 4 is exactly 2. Now we must carefully evaluate 4 to the log base 2 of the prime number 5. We can cleverly rewrite the starting base of 4 as the number to squared again. We essentially have to squared raised strictly to the log base 2 of 5. We simply multiply the inner and outer exponents together to fully simplify this. It becomes 2 to the power of 2 multiplied by the log base 2 of 5. We can move that multiplier of 2 inside the logarithm function as an exponent. It becomes 2 raised to the log base 2 of the mathematical quantity 5 squared. 5 squared means 5 times 5, which is equal to the number 25. We currently have 2 raised to the log base 2 of the number 25. The exponential base 2 and the log base 2 structurally cancel each other out. This entire complicated-looking term perfectly simplifies down to just 25. We now simply multiply our 2 separately calculated mathematical parts together. We multiply the calculated 25 by the calculated 2 to get exactly 50. This firmly means that the expression 4 to the power of x evaluates to 50. The original given equation was 4 to the x plus 4 to the x equals 100. We confidently replace both of these identical exponential terms with the number 50. 50 added to 50 is indeed strictly equal to the target value of 100. Both sides of the algebraic equation match perfectly and without any contradictions. The exact mathematical solution is fully confirmed and perfectly verified. Thank you very much for taking the time to watch this full algebraic breakdown. Please hit the like button and actively subscribe to the channel for more math videos.